We can set it up real quick if you want. Okay, I just want to double
Chelsea was there. Chris wasn't there.
Okay. What was
Yeah, it's way better than
yeah, I didn't want to do that. Yeah. But it's not like, so yeah.
We'll move.
Can you tweet?
Do I have Marco's permission?
Does she have your permission to tweet? Okay, so thank you for coming. We have a few minutes to ask me questions about Marco. So what do you want to know about Marco?
You know why he's wearing sunglasses?
Yeah, why is he wearing sunglasses? I don't know, Marco.
Just prevent the high contrast light in the document.
I guess too many photos come first, right? So one thing that I can definitely tell you that like other illustrious, famous people, Marco liked beer in college, okay, but once he moved to grad school, he liked it even more, right? So that's, and there are other things that are better left unsaid. Something that I would like to say is that he was incredibly productive. He came in 2014, and he's just a little bit more than, he joined in 2014, and in a little bit more than 5 years he produced countless papers, and it's literally countless because I can never remember how many he has. And after he leaves, there will still be, so that's at least 5 or 6. One to be submitted soon, and there is still a couple that will have to happen after he's done. So I guess one defining quality about Marco is that he's the most courageous student or individual I've seen, or scientist, in the sense that he would literally do anything. And anything I would suggest to him, which I would forget about 2 hours later. 3 days later I would remember, maybe, and I would ask him, so you remember we were talking about that? And he'd say, yeah, I've done it. So he went to a range of projects, techniques, from imaging, electrophysiology, computation, and all that. So today he's going to talk only about the tip of the iceberg, I should say, or one of the latest projects that we approached, and his slides are very new, very fresh. I don't dare say how fresh they are, but they are fresh, as in they have been done very recently, Marco, right? So he's going to talk just about that. As far as his career plans, you can ask Marco after his talk, or you can talk to him later. One last thing I wanted to say about him is that he is not only courageous and stubborn and driving people crazy, but he's also a very generous person. He actually trained countless numbers of undergrads. Some of them are here. Also some graduate students. And we have all learned from him, including myself and other people. Okay? Anything else you want to know about Marco? No? Then here we go, Marco.
All right. All right, thank you guys. I'm not used to talking on the microphone, but move that down. Okay. All right, so today, like Lauren said, I want to just talk about a brief story that we've been working on in the last few years or so to kind of just give an overview of what I've done and what has. Okay, so our lab focuses on ion channels. So ion channels are, of course the video is not going to work. So ion channels are tiny little membrane proteins that are span the membrane and allow the passage of charged molecules across the membrane, and they are stochastic processes that open and close due to voltage. This video is supposed to open and close and show single channel recordings. Ion channels encompass the overall activity of neurons, and neurons are then composed of networks and organized in different networks such as the pre-Botzinger complex, which I'll be talking about later, and different architecture that makes up the brain. That overall leads to the production of a certain behavior, and that behavior that we're interested in is respiration. So in general, these ion channels regulate the flow of charged molecules that dictate the activity of neurons, which then encompass the whole activity of networks to drive the behavior. Respiration, I hope you guys are all breathing today. I'm going to take a big breath and try and relax a little bit, activate my pre-Botzinger complex so that we can get this going. So I first wanted just to give an overview of the approaches on different types of projects that I've done. So the first major project that I've worked on was working with a bunch of undergrads and Lauren to design a software that integrates the positional data from our scientific instruments to create a 3D virtual environment that will display the view of a live image and where you are within a larger context of the slides, in a nice software package that can help users, enhance the user experience to help learn how to patch and to automate some processes. The next big project that I've undergone is developing some algorithms for model fitting. So ion channel models have very complex data sets that require sets of algorithms to optimize a set of kinetic parameters so that the model can output a certain behavior. The majority of most of my work has been doing electrophysiology and imaging. That would be involving single electrode whole cell patch clamp recordings. Here's just showing some calcium imaging data as well. And the last major hurdle would be real-time computation. So real-time computation is basically taking the advantage of an ordinary differential equation solver to basically solve your models and test your model in real cells. So this is just a basic recording setup where you have a patch or a pipette onto a single cell, and you can record the voltage and inject a current. And the current that you inject in this mechanism is calculated based on a model. And that model can be changed in real time to try to test many different ideas that will go and really let you know whether or not your model is functionally relevant. Because if you have a model and you can't really mimic what you're actually trying to reproduce, there's really not much point in having the model anyway. Okay, so I wanted to go on about the model system. So we use the rodent as our model. So here's a picture of a neonatal rat brain. And we use a vibrochrome and some gross dissection to remove a slice of the medulla, or the brainstem, which is located in the back of the brain, that controls a series of pacemaking circuits that are important for respiration. So this is what it's about a 350 to 400 micron slice that contains a series of networks known as the Klebsian complex, which is a part of the brain that's named after a winery in Germany. The raphe neurons, which sit at the seam of the brainstem and secrete serotonin throughout the brainstem. The most identifiable feature is the inferior olive complex, which is important in auditory processing and how auditory processing is coordinated to the cerebellum, and as well as the 12th motor nucleus, which is important. So these preboscenior neurons project to the motor neurons, and these motor neurons are the ones that run out the nerve towards the actual muscle and synapse onto the muscle, so that you can actually get contraction. So within the slice, there's a series of networks that maintain their rhythm with when you apply toxins to the back. So these types of behaviors are the preboscenior complex, the PBC. These neurons burst, so they have a series of about 20 to 30 action potentials, all within a time frame of about a second, and then there's a period of quiescence met on by another series of bursts. These bursts are important to have rhythmic contractions of motor coordination of the muscles. And then the ventral raphe, they're pretty boring compared to the preboscenior complex, but that boringness comes into play into how their ion channels are. So I want to talk about a little bit about the serotonergic system, because I do study some serotonergic neurons. So here is a projection of the main serotonergic neurons. So there are the dorsal raphe, and these dorsal raphe sit within the midbrain. Here's the cerebellum, the forebrain, the brainstem. So the dorsal raphe sit in the midbrain, and they project all serotonin all throughout the forebrain, including the hippocampus, hypothalamus, amygdala, which is responsible for fear, olfactory bulb. But I study the ventral raphe. And the ventral raphe are located in the brainstem, and they project to the autonomic systems within the brainstem to help modulate the activity in general. So The serotonergic system is implicated in many different disease states. So if you knock out the tryptophan hydroxylase, animals become very, very aggressive, have problems regulating their mood, and then oftentimes diseases that lead to depression have some dysregulation in their serotonin processes. And in order to treat them, SSRIs, which are selective serotonin reuptake inhibitors, are used often to help increase the amount of serotonin in the blood. Ventral raphe, so they're more important for autonomic regulation, so motor function, breathing, and the ventral raphe are implicated in a disease known as sudden infant death syndrome. So sudden infant death syndrome, also known as SIDS, is a disease that encompasses about 80% of all children that die, or all the children that die before age 1 for basically any unknown reason. Most of the time the cause is respiratory regulated. So basically the infant just dies suddenly during their sleep because they stop breathing. So here's just a cool data set that is showing that since it's SIDS and they die at an early age, and it's very hard to get a good control to compare. But this study was able to find some controls through some other data sets, and using 2 different methods such as ELISA or HPLC, which is high performance liquid chromatography, they've measured that SIDS patients have an upregulated amount of serotonin in their blood. This actually, there's plenty of other studies that go on to talk about how there's dysfunction, so less overall tryptophan hydroxylase in SIDS patients, as well as lack of receptors in the patients. So overall, the serotonergic system seems to be implicated in the sudden infant death syndrome. So congenital sleep apnea is another rare, much rarer disease, but it still requires serotonin in these neurons to be functioning in order for that. Not click too many times. None of the videos are going to work. That's fine. Okay, so back to the system. So here we have the respiratory slice, and I mentioned that the serotonergic raphe are the neurons that I'm interested in. Their output is basically a tonically firing output, very kind of boring in a way to look at, but it doesn't really change. It fires about 2 times a second, 2 to 3 times a second, and when CO2 is increased in the blood, they actually kind of increase their overall firing rate. So these raphe neurons have lateral projections to the Breed-Botstinger complex, as well as the 12th cranial nerve output, and that can modulate the activity of the raphe neurons, can modulate the overall activity of the respiratory system. So here is the output of Breed-Botstinger neurons. So we have some nice bursts of action potential, and then when we stick a pipette just above the pipe of the raphe and increase the overall potassium concentration, that will drive activity in those neurons. We actually see the activity of the Breed-Botstinger complex actually increase, and that's a reversible process that can return back to a normal state. Here's just another type of experiments done from Matthew Hedges and George Richardson's lab, where AMPA, which is a glutamate agonist. So glutamate is the main excitatory neurotransmitter in neurons in mammals, and when you excite the raphe with AMPA, we see the 12th nerve output have an increased frequency, showing that the activity of the raphe can help regulate the overall activity of the Breed-Botstinger complex and the whole network. So these raphe neurons, the raphe means seam. if anyone is interested, the seam is because they line the midline of the brainstem. And these neurons express serotonin, tryptophan hydroxylase, as well as a molecule called substance P. And both substance P and serotonin are excitatory to the respiratory circuit. So this same experiment can be done with substance P, injecting substance P, and that will increase the overall activity of the respiratory circuits. Okay, so the central question to my dissertation basically is how do ion channels help regulate neuronal firing? And with that, we use the idea of the sodium channel. This is the crystal structure of Navarro, which is a bacterial sodium channel. That's the best crystal structure that we have of the sodium channel and some sodium channel currents. How do these ion channels and the expression of channels within the neuron help regulate the overall neuronal activity? And the activity that I'm mainly going to be talking about is the rapid neurons. But I have studied a few other neurons as well. Okay, so I wanted to teach you a little bit about some molecular kinetics. So I thought about describing using the concept of a Lego man to help describe that. So we've kind of all played with Legos. They're little people that can stand up and down. And functionally, this cheap Lego man, this Lego man can only sit down or stand up. In between doesn't really happen. But these two states are the functional states that have some function to them, and they're governed by a set of transitions and the rate between the rate of that transition. Of course, as I mentioned, there are a continuum of different states that can be occupied between the transition of sitting down to standing fully up, but sometimes these transitions cannot be identified, nor are they potentially stable, and therefore we try to only use the ones, the states, signify the states that can be truly identified. So for the case of an ion channel typically functionally has two overall states. So we have a closed state and an open state. From the structure, we know that the whole protein is made up of 4 homologous domains, each with a voltage sensing device that has positively charged amino acids that can translocate within the membrane to allow the opening of the channel. So when the channel is open, there's no pump, there's no energy going into the system to drive ions across the membrane. It mainly uses the established gradients by the pumps to allow the passive flow of charged molecules. And this is the case of the sodium channel. So if we think of just the C is made up of lots of sodium chloride. That's very involved in the C, so the outside of the cell basically has a lot more sodium, and thus the flow of the molecules is typically down the electrical chemical route. So we know that an ion channel, the activity can be described by 2 different states, as they can be functionally identified through single channel recordings. So with the discovery and implementation of single cell patch clamp electrophysiology by Fred Zachman and Nair in 1990, which won them the Nobel Prize in 1981. We can see that there's with the resolution that we can get and enhance the signal to noise ratio, we can actually see clear openings between a closed state, which is the baseline on top, and very fast openings that are going to a single level, a single conductance level, that if we had more than 1 channel in the patch, we would actually see 2 levels. If we had 3 channels, we would see 3. But once you get to 3, it's very hard to detect how many are actually there. So ideally, you want to find some recordings that have a single channel, and with that single channel, you can determine the rates of the transitions between the closed state and the open state. So this is done when you're in an on-cell configuration. Most of my recordings are actually done in a whole cell configuration. And what that means is basically I enter the on-cell configuration, and then I apply a sharp pulse with my mouth, or like a flick on the system that applies like a sharp rupturing within the membrane, and that will actually create a continuous flow from the pipette to the cell. We see how there's dye is loaded into the cell there, and with that we can actually record from all the channels within the neuron. So here, from that single channel recording, we see that this is a recording from tens of thousands of channels. So the current that would flow from a single channel is on the order of picoamps. That's 10 to the minus 12. That is a trillionth of the amount of charge that it takes to charge your phone. But the currents that actually drive neurons from happening require the coordination of thousands of channels so that they can actually reliably maintain a message. So this recording from thousands of channels, you can record currents from 2 to 10 nanoamps or so, depending on. Okay, so of course, channels can be described with the simple states from their structure, as well as plenty of other experiments that that have been done in the past. We stand on the shoulders of giants. We know that there are other states within the channel. So, as I mentioned, these channels are homologous proteins with 4 homologous structures. Each structure maintains an alpha helix of positively charged amino acids separated by every 3 amino acids, so that on the alpha helix there are positive amino acids that are pointed outwards, and that has been shown to actually translocate or move within the membrane before the channel actually opens. And with some interlocking experiments, we've shown that all the voltage sensors must activate before any ionic current actually flows. So in order to describe those kinetics, we show the activation of a single voltage sensor is defined by a certain rate. Then we actually try to constrain our model so that we limit the number of parameters that we have, so that the same activity to activate one voltage sensor is then used to activate 2, 3, and 4, and so on. This process is also voltage dependent, meaning that if you apply voltage stimuli, the overall activity changes depending on the voltage. So what we saw here is that the process of activation, so we have going from a holding membrane potential, let's say pretty low, around -80, around resting membrane potential, and we depolarize the cell to different levels at about 5 millivolt increments, and we see that there's an increasing amount of current. That can be described by a sigmoid. With that, we can fit it to a Boltzmann equation, define certain parameters such as the V-half of activation, which can then be used to compare different channel models or different ion channels with the cell. So with sodium channels actually undergo a process of inactivation, and that actually can be seen within this activation trace. So if sodium channels did not have an inactivation, we would see that the current would stay on for the entire length of the protocol. So instead, we see that within a time frame of about 5 milliseconds, the current becomes inactivated, or there basically is another part of the protein within the 3 to 4 intermembrane loop that comes in and blocks the pore from the inside, and that helps allow the action potential to travel down. This process of inactivation is also voltage dependent, which can be measured by a series of voltage clamp pulses. And in this case, it's basically the opposite of activation. So we go from changes in lower membrane potential to the same membrane potential, and we see that the process starts at the maximum, which is around -80, -100, and as voltage increases, we get a decay in that process. And that process can also be described by a Boltzmann equation, and so forth. So this is a kinetic mechanism as it can describe a series of transitions that the molecule will undergo, as well as the rates between each transition. And in order to find those rates, we use different algorithms to help calculate that. Each individual rate, since these are voltage-dependent ion channels, have a pre-exponential factor as well as a voltage-dependent factor. Because these rates, if, say, from this bottom trace to the top trace, there's a very large voltage shift, that would drive these forward voltage sensors upwards much more faster than a much smaller voltage. I hope that makes sense. Okay, so sodium channels, what are they and what do they do? So sodium channels are required for the activity of neurons. If you apply a toxin called tetrodotoxin, if you inject it into someone, that can literally kill someone. That is because these sodium channels are required for muscular and neuronal activity. So sodium channels have a high density in the axon initial segment, and that allows these channels to basically maintain a lower membrane potential so that they can easily be excited. And sodium channels are required for fast pacemaking. They can control the frequency of overall activity of neurons and can regulate some complex spiking patterns. So there's the superthreshold sodium channel, or sodium current. That is the main current that most neuroscientists are familiar with, as the opening of channels helps drive the membrane potential up the upstroke of the exponential. At the top of the exponential, sodium channels are inactivated, and that allows the flow of potassium to basically bring down the membrane potential back to repolarize the membrane. But there are also subcurrents that operate within the subthreshold voltages, and those are kind of what I'll be talking about a little bit today, as they can help regulate the overall activity. So, in the last slide, we talked about this kinetic mechanism and what the rates are in states to regulate the activity. So during a normal exponential, what happens to the probability of the occupancy probability of the states is that at low voltages, the depolarization will drive channels from the closed state into the open state and then quickly inactivate. And that helps drive the upstroke of the exponential. But during the inner spike interval, that's basically when the probability of the inactivation is able to recover so that the channel can become available to open yet again. So there is, so within the serotonergic graph, their sodium channels undergo a frequency-dependent modulation that is decidedly a little bit slow. So what we have here is a voltage clamp trace where we apply 20 stimuli at different frequencies. So here's 5 hertz, 10 hertz, 20 hertz. Hertz is just a unit per second. So we apply the pulses every 5 times per second, and we, using a series of toxins, to block the other currents within the cell and to truly isolate the sodium current, we can measure how the sodium current responds to the overall frequency. As we see, when we increase the overall amount of frequency, the total amount of inactivation, or the overall available, the inactivation is increased and the availability is decreased. So this is basically describing how these channels enter into a state of inactivation. And when we want to try and measure the opposite, or how these channels recover and return to the overall resting state, we can apply a series of 2 pulses separated by increasing exponential in time. We can actually measure, there's a fast rate of inactivation which typically happens within the first 50 milliseconds. And in some neurons, is completely done in 50 milliseconds, but in Raphe neurons, it takes about 6 full seconds for these currents to fully become available again. And that 6 seconds is crucial in understanding how these Raphe neurons can regulate their overall activity. And this 20% here is, so basically, if you plot the recovery of this process, we have a single exponential. This is an exponential in time, and this is just availability. There are 2 exponentials that we see here, indicating that there are 2 potential processes that are regulating this mechanism. So this fast component is over and done within 50 milliseconds, and then that plateau phase of where this slow mechanism takes over is about when 80% of the channels are available. So this last 20% undergo a process of slow recovery, and that takes in total about 6 full seconds to recover. So when we try to record voltage clamp data and fit a model to these experimental behaviors, the model that I described to you does not fit the data. It cannot, no matter how hard I try and no matter what rates can these states actually occupy, this model cannot explain the use-dependent availability of sodium channel, nor the bi-exponential recovery of sodium channel. In order to do that, you must add another state that we added to the open state due to some other evidence that I'm not going to be talking about today. But that other state, we have a fast entry and a slow exit from that state. That allows the model to basically take back a few of the ion channels from being available so that it can actually explain. So these data were obtained using voltage clamp protocols, and that model can fit a series of voltage clamp data that go from activation, inactivation, deactivation, entry into slow inactivation, all sorts of different molecules. You want to be able to test many different voltage protocols so that you can force the channel into as many states as possible. I just kind of wanted to talk about how that process is actually done. So this is just a screenshot of the modeling process in the program that we use called Cube. So Cube uses these Markov models, or these state-based models that we can see here, defined by a series of rate transitions. And it uses its own kinetic programming language so that you can designate different behaviors. So within this main script, you just define this bunch of parameters. And within these tiny little buttons here, that's actually what's doing most of the work. So in order to fit all of this data, what we actually have to do is we have to take the model and simulate the model to the same experimental data that was used to acquire this data. So what each of these scripts actually does is that it takes that model and actually simulates the protocol, and then it analyzes the data and outputs it on the graph. So the actual calculated data is in red, whereas the fit data that we want the model to fit to is shown in white. And what this does is that there is an algorithm called the optimizer that uses a gradient descent method to basically modulate the rates. Once you modulate the rates, you calculate the response of that model to the response of the protocol. That will then generate the response, and you can then calculate the difference between the output of the model to the to the actual experimental data, and then perform a cost function fitting analysis to figure out how different they are from each other. And then the optimizer, what the optimizer does is basically tries to reduce the total amount of error between the experimental data and the model data. So all this process goes through iterations of probably like 20 iterations for each actual iteration. But in a time frame of about 45 minutes, you can take a model with many different topologies and produce a model with a certain behavior. And my second chapter of the dissertation talks about some model constraints that we've helped implement and design in Q to help improve the modeling process. So here's just a pictorial diagram of kind of how that goes about. So say we have our experimental data and we want to produce a model that replaces or mimics the experimental data. So that experimental data can be defined by a parameter space, and that parameter space can be simply the actual rates of the transitions between each model. So this parameter space is then converted into a free parameter space because performing the optimization, it requires a model blind, or it performs the operation model blindly. So we convert the set of parameters into a free parameters. But this is just showing a parameter space of 3 for a simple model. Then we apply sets of constraints. So in this example, we've shown equality constraints. So that could be simply scaling one rate to another, such as scaling the rate of 1 voltage sensor activation to 3 times the rate of 3 voltage sensors to activate. And by applying an equality constraint, that can actually reduce the total number of free parameters. So from the cube of 3 parameters that we went to, we now are in a square, as 1 parameter is now missing from the overall model. The second set of constraints that were performed are inequality constraints, which basically reduce the parameter space to a certain set of data. So instead of necessarily saying one rate is equal to another, we can scale the rate. 1 is less than 5, or we know from someone else's data that the activation time constant is faster than 5 milliseconds. So then we can apply an inequality constraint that on a specific parameter to overall reduce that parameter from going and obtaining certain values. The last set of constraints that we've developed to help improve this whole modeling process is a set of behavioral constraints. So it's kind of clear from all these talks of data is that these rates might not actually produce a model that has a desired behavior. Many of these rates this model can produce something that's close, that kind of mimics the actual experimental data that we have, but sometimes it might produce something that doesn't look anything like what you want to do. So what we've implemented is a set of behavioral constraints that modifies the cost function so that it adds a certain penalty parameter to basically test whether or not the output of the model produces a certain behavior. And this can undergo through a flow chart here. I'm not going to fully describe that, but that is basically how one can implement these behavioral constraints so that you can produce models that incorporate many different types of data. So this, the most useful one of this is combining single channel data and wholesale data, because every time I've done wholesale, I have to pop the membrane, and that basically eliminates the possibility of doing single channel data. Well, with this capability, you can take single channel data from, say, another lab, and that deduced that whole term to a probability of being open, and then we can use that data and modify our model so that it can reliably produce that behavior. Okay. Take a drink of water real fast. So as I mentioned before, what good is a model if you don't test it? So ideally, we want to be able to test these models, and what we've done to actually do that is implement dynamic clamp. So dynamic clamp is just like current clamp, where the actual cell is integrating some of the unknowns that we have from the channel. So here is just a basic exponential description of a neuron. So we have a sodium current, calcium current, potassium current, a leak current. All these are unknowns, but with our model, we have the model is just the sodium channel. By testing it within a real cell, we don't have to estimate what those actual values are, as the cell simply has those channels and already innately expresses them. So it eliminates a lot of unknowns from the equation. What I've also done is, instead of just a single compartmental model, I've also, in a different work, basically create a long multi-compartmental model to examine how the distribution of channels in one compartment or another compartment further along can help change the overall output of neurons. So here is just an example of just a simple control and a model-induced model. Most of these dynamic clamp experiments utilize the activity of the pharmacology so that the tetrodotoxin blocks all the sodium current and only the sodium current. So we can take advantage of that by applying the drug, or recording the sample, applying the drug, and then testing our model. And then comparing before and after to see how that describes the data. Okay, so back to the concept of long-term inactivation. So we talked about, in general, how the kinetic mechanism of the ion channel, during the peak of the exponential, channels are driven from the closed state into the open state and into this fast inactivated state. And then during the inner spike interval, the channels then return towards the closed state. So what happens during that brief depolarization when when there is a presence of this long-term inactivated state? So this S state, as I mentioned, it can help explain the bi-exponential recovery or the use dependence. So what happens during this brief depolarization of about 2 milliseconds, which is the length of an exponential, what happens is the probability of closed plus open, is 1, but that probability goes down as we enter from the closed into the inactivated state. The probability of opening slightly increases, and then it decreases as an activation takes over. And the probability of inactivation increases to a certain level. But if we plot the probability of this inactivated state, we see that in a brief depolarization, it sends the overall probability to a certain level. And if this time was extended to infinity, this probability of S will actually reach a much, much higher level. But this process is slow, so it only reaches about 15 to 20% of the actual maximum during the fast depolarization. So during a repolarization, so basically when the peak goes down, what happens is that all the channels that were inactivated basically become non-inactivated again. So they return from this inactivated state back to the closed state. But the channels that were in this S state still slowly return back to the S. and then eventually go back to zero. So this is just trying to describe the overall occupancy probability of how these, what is actually happening with the model during a simple brief depolarization. So what we want actually to do is to describe this process in a mathematical description known as a leaky integrator. So one of the best leaky integrator examples would be a river drain, or basically raining into a lake, which the lake then has a river or a waterfall that goes downstream. So basically, as water enters the lake is, the river is all, the total level of the river is still falling as the rate of the river fully decreases. So in the case of a sodium channel, what we use as an integration is the probability of the S state. So the S state can, basically with each individual brief depolarization, only a small proportion of the channels enter this S state, so that if you increase the total frequency of the stimulus, you can, the probability of the S state will respond to that overall frequency. What the input is simply voltage. So how is this actually tested or implemented? So here we just applied simple voltage steps to this leaky integrator model at different frequencies, 2, 5, 10, up to 100, and try to look at the overall probability of how of the state occupancy of the S state. And then what we did was we modified the rates between the open state and the slow state to see how, if you add more leak or you subtract more leak, how will that change the overall response of the model. So in red here, that's basically our, white is our control without long-term activation. So red is the control. We see with each pulse, it slightly increases the probability of the S state as we see here. And then slowly over time, that probability will slowly decrease. If we increase the rate or the leak of that entry, the channels still accumulate into the S state, but that overall accumulation is reduced. Okay, so this describes how neuronal spiking frequency affects the sodium channel dynamics, as a simple exponential can send this sodium channels into this S state. But do sodium channel dynamics actually affect the neuronal firing and neuronal spiking? So to do that, we've done some dynamic clamp experiments where we inject the sodium channel model and just the sodium channel model. We've changed plenty of different types of models, but here's the one with the LTI model, the long-term inactivation model. So what we see here, 4, 8, and 16 are just increasing the overall amount of sodium channel conductance that we have. And this is the actual cell's response. And this is the calculated current. And what we see is when we increase the conductance, we do see an increase in the amount of current, which is not really, which is expected. Not surprising. That also correlates to an increase in height of the exponential, which is also not expected. But what we want to see here is how does this increasing the conductance change the overall frequency? What we see is that increase in the conductance has a practically linear proportion within the first part of the range. That conductance is proportional to frequency. And if we align all the exponentials to the peak and then compare where they respond, I said before, the red is the max, white is the first conductance. So the red is much, much higher. But the response, so since this is in a living cell, the response to the overall activity is mainly the same up until a certain point. So at minus 53, that's when these currents go from the subthreshold to superthreshold, so between minus 53 and when the exponential is actually initiated, that is proportional to the total amount of conductance. So what we see with the low amount of conductance in GNA equals to 4, we have a very long spike interval, whereas if we increase that overall conductance, the rate from that voltage is driven to much higher potentials and reaches the overall activity much, much faster. So overall, the sodium channels do drive neuronal firing frequency, and that kind of completes the loop. So what this is basically describing is a negative feedback loop for which ion channels, and the sodium channels in particular, can describe and maintain a steady output in the cell. So just like your thermometer at home, if the temperature goes too low, you increase the total amount of heat that is produced so that it can increase the amount of temperature that we have. So the measurement that is taken is frequency, and we've shown that the probability of the S state is proportional to the overall frequency. So if frequency increases, that increases the amount of the S state, which then reduces the overall amount of sodium current, which is the process variable. As the sodium current increasing or decreasing, the overall current can change the frequency, and then that returns back to a certain baseline. So in the case of the Raphe neurons, when the system increases the total amount of carbon dioxide in the system, the cell responds by increasing the firing rate, by increasing the overall amount of serotonin to tell the respiratory system to basically keep breathing. But that increase in frequency is sensed by these long-term inactivating channels to help return the channels back to a nice set frequency that they typically fire at. This description can be also described similar to just like the thermostat with an engineering controller. Here we use a PID, which is basically an integrator to account for different errors within the system. Basically, this is all done by the sodium channel. So another section of my dissertation that is a little bit more, takes more time to actually fully explain, is trying to understand how this measurement is actually sensed and what can actually be the signal for the molecule to regulate frequency. We think that this signal can potentially be intracellular calcium through means of calmodular regulation. So I've done plenty of voltage clamp experiments under different intracellular calcium solutions and find minimal differences between steady state inactivation and normal firing properties, but the use dependence, which is what would be most modified by this regulating mechanism, it does seem that the high calcium solutions do have a lower, they have less long-term activation than the low calcium solutions. So it's still a little bit unclear how this calcium actually maintains the set point, but that will be work for someone else or someone down the road. So some conclusions and some future directions. So intrinsic pacemakers, they rely on ion channels to help establish overall rhythmicity. Sodium channels in Raphe, they have some frequency dependent inactivation that basically removes a set of channels from the overall availability to help reduce their firing rates. This sodium channel can be described via the molecular linking integrator I just described, and that regulation can potentially be regulated by intracellular calcium. So overall, if these RAF-A neurons are setting the total amount of serotonin within the brain, this mechanism could potentially be targeted to help either reduce or increase the overall levels in certain disease states. So I do have some thank yous to just thank for the work of the dissertation. So I first like to thank my mentors, Lauren and Morella. They have been headstrong all the way and have basically taught me all there is to know about the field of biophysics and neuroscience. I would like to thank my committee members, David Scholes and Kevin Gillis, for their help along the way and trying to get started and bouncing ideas off of. I would also like to thank Dr. Mike Hannick, John David, Dr. Garcia, and Natasha Davis for their help in the first few years, basically through the IMSD and the Gus Reidel Fellowship. They've gone through, I've sat through many different lectures and descriptions of teaching you how to read a paper and actually criticize science and whatnot, and that helped a lot in overall development. As far as the lab mates go, there are plenty to be named for. I'll first mention Atusa. Atusa was the first grad student. She was the first grad student there. She was the, she trained me to do all sorts of many different things. Benton Barrican, he basically ascended the role from a undergrad into a grad student, become a great colleague. Marzi has been fantastic to basically bounce ideas off of and get through all the way. I have some collaborators who helped with some data analysis as well as bouncing ideas off of. And then, of course, plenty of NU staff. Of course, would like to thank Debbie Allen and Nyla Emmerich for all their help throughout many years, as well as Alan Marshall, so that he has called him many a time late when he was in meetings, has always been willing to help and whatnot. Life support, basically, these are some of the names of all the people that have helped keep it going. And yeah, thanks. Oh, and support been funded by the Department of Education GAN Fellowship. The lab is funded by, a lot of the work was funded by American Heart Association, National Institutes of Health, IMSD Initiative, and the Gus Reidel Fellowship. Okay. Thank you. Also, we have lots of beer.
Okay, so just a few questions, and Mark will be around for 2 more months to ask more questions.
So, do all these states actually exist, or are they required within the model because of the way you describe how you shift from one state to another? In other words, if you had a different description, mathematical description of how you could move from one state to the other,
Yeah.
would you come up with a different model?
So the model was designed with structure in mind. So I believe all these states do actually exist, and there is some functional data with voltage clamp fluorometry to explain whether or not these the voltage sensing domains to actually integrate and move independently with voltage prior to the ionic current establishing. So I believe most of the states with or all the states within the main kinetic model that I've described, I believe do exist. In order for them to fully describe the data, if you so that chain is like 8 states, if you truncate it to just 4, you still can't fully capture the use dependence of the model. So they are required in order to fully describe all the kinetics. You could potentially find a different set of parameters that may be able to describe all the data, but based on all the voltage clamp data that we have, I don't think you can describe all of that with a simpler data set or simple model. Yeah.
Okay, can I ask a
So the
follow-up?
answer is yes.
Yeah.
Okay. So is a given model unique with so many different degrees of freedom?
Uh-huh.
How do you know that that's, the model you come up with is the only solution?
Of course. So you can never really know, and it's only as good as what you do with the model to actually test it, or at least make some use of it. So in applying the mathematical constraints overall to try and reduce the total amount of free parameters, that should always be done to try and reduce the number. If you can. And of course, the modeling process is never just, we ran the system once and we got an output and we say, yay, woohoo. It is a reiterative process that retakes multiple topologies as well as multiple initial starting parameters to fully find a function model.
I think I'm just rephrasing Andy's question.
Okay.
But were there any specific behaviors you observed that could be described by the 13-state model that couldn't be described by the 5-state model? Because it seemed like in the beginning you started with a 13-state model, but the 5-state model seems more important.
So we just use the 5-state model as a pictorial description.
Yeah,
to
well, that's how
simplify
I think
the
about it, but I'm
description,
looking
yeah.
at the macroscopic.
So
did you see intermediate conductance states, or that wouldn't be affected by it because you only have one open
For
state?
sodium channels, I don't think there's any evidence of intermediate conductance states. I know for like calcium activated,
But I
any
mean,
sort of
in
channel
your
can-
observations.
yeah, no, I have not seen different conductance states.
Okay.
And most of the time, we use the 13-state model or derivatives of that model to perform dynamic.
Would it be fair to summarize, just kind of following up on this again, you have lots and lots of states here, but you also have lots and lots of constraints.
Yeah,
And,
of course.
it appears at first glance, when you look at a 13-state model, that there's all, 26 free parameters or whatever, but that's not actually the case.
No.
A good part of your work, if I understand correctly, is finding, methods to solve for greatly reduced parameter sets.
Exactly.
Is that a fair term?
Yeah, for the 13-state model, if you don't have any constraints, there's I think 48 total parameters that could be described for that model. But with all the actual constraints implemented, I believe the total is 22 or so, which is still pretty high, and it's arguably potentially find all those values for that. But yeah, like Dr. Gillis said, it's best to try to find mechanisms to reduce the overall number of parameters. Yep.
Let me rephrase my second question.
Okay.
You do some kind of search algorithm to optimize this?
Yep.
Okay, so if you start in different parts of the parameter space,
Yeah.
you always end up in the same solution.
No, definitely not.
You
If
don't?
I mean, if you start with terrible starting parameters, you can get trapped into, you can find, I mean, it might start searching down the wrong path. If the possibility if it's still within the overall, ideally, yes, the answer should always be yes. You should always find the same solution. But if you start further and further away from the actual optimal solution, within the time frame of your modeling experience, you might never actually.
But there is a global minimum.
There is, yeah, of course, there always is a global minimum, and it will always try to find that, but.
What I'm
it doesn't
basically
always
asking, is there only one minimum?
Is there only one minimum?
Don't say yes.
Yeah, there are many minimums for many functional states, and there are functional states change time and space. It's
I know that you always ignore me, so I was the last one. This is an inside joke. So just following up on this question, so about the 13th state, the slow state, right?
Yeah.
So from all your data and all the, considering the biophysical evidence and experimental, so that state seems that exists. Is there any other experimental evidence that that state is important and exists from other labs and just to
So the phenomenal, not the phenomenal, the molecular identity of that potential state could be, we've identified that and we've tried to probe with some experiments that function, the interaction is called a fibroblast growth factor, homologous factor, which is fibroblast growth factor, which is not secreted and actually binds to the C terminus of the voltage-gated sodium channel, and it co-localizes with just about every single sodium channel you can find. So functionally, some isoforms of that protein have been shown to produce the overall behavior in heterologous systems. So I believe that blocking state, which could potentially be this molecule in these neurons, I believe it exists. What I've done to probe that interaction is using an antibody against that to try and see if that can block the actual activity. It's had some mixed results. I think it's kind of working. It's just hard to fully convince yourself of whether or not it's an actual kinetic phenomenon that's going on.
so there is some molecular interaction and explanation of that state. It's
Yeah,
not
there
just
is it's not just a random,
model.
no. There is some other molecular descriptions of that. So. Yeah.
Is it location specific? Is it specific for some voltage or sodium channels, or is it something that?
The long-term activation, yes, it seems to be highly pertinent for NAV 1.4, NAV 1.2, or 1.6. It has been shown to bind to NAV 1.1, 1.3, 1.2, 1.4, not 1.5, 1.7. No, I don't think it's the other twos. So it is isoform specific. It is also functionally specific. So some cells have it, some cells don't. And the activity of all these channels can change depending on whether or not the location of the channel is in the axon or further down the axon. And I did not describe any of the location information like that, just because there's too much outside.
So Marco, so what types of neurons would you expect to have this property long term?
The slow type 1 firing neurons that,
Why?
because having the long-term activation property that is kind of like the cell mechanism to maintain a steady firing rate. So like the fast firing cells of like the Purkinje neurons, I don't believe
They also have a steady fire.
Yeah, they do have steady fire rates. So yeah, pacemaking neurons and I think slow firing neurons would mainly have it.
Fine, maybe one last question.
I was just curious, we were talking a while ago, like, did you ever just dump a big old calmodulin inhibitor on it and just saw how that affected this slow activation?
Never did that experiment, no.
Okay.
Yeah.
I know you can't do everything, but it'd be cool to see.
Yeah, I've delved into some calcium caging, but I never was able to find some functional activity with that. So. righty, well, thank you guys for coming. I made it.
Hello. How's it going?
Oh, mira, está.
It's the same as before, I submitted it.